In this video, I want to talk about parent functions and their transformations. A parent function is like the most stripped down version that still keeps of a function that still keeps its quality, its shape, its properties. So they're not going to have any things tacked on to it. Okay, and I want to go through 5. Okay, there's many more than that, but these are 5 very common ones. 2 are polynomials, and they're inverse, and 2 more are their inverses, and then the absolute value function. The first one here that we have on our right, now this is a quadratic function. Okay, quadratic. And its shape, okay, the shape of it, it makes a parabola. Okay? It makes a parabola. That's what this, and a parabola is not just any U-shaped thing. It has very specific properties that you'll learn in pre-calculus. You'll learn a little bit of it here. But this shape is called a parabola. Okay? And you notice it's symmetric about the y-axis, okay? If you flipped it on its side, it would be symmetric. Or if you flipped it over, if you took this piece here and flipped it over the y-axis, it has y-axis symmetry, so it would overlap. And its equation, okay, of the parent function, okay, with an vertex at the origin is f of x is equal to x squared. Okay, these might be familiar to you. We've calculated the zeros of these things, and you'll notice that this is very, very stripped down compared to things that you've seen when you deal with factoring. Okay, a few other things I want to talk about are the domain and range of this function. So the domain is all of the x values that can be plugged in here, okay? So the domain, if you think about this, what x values can you plug in to this function if you think about it algebraically? Well, you can plug in any real number you want into this function, okay? Graphically, it's kind of what does this function, what kind of shadow does it cast on the x-axis? And this thing keeps on spreading farther and farther outward from the y-axis, okay? It goes in this direction and in this direction. It keeps on spreading. So it's going to create a shadow everywhere on the x-axis, meaning every x value that you can plug in has a corresponding y value. If you plug in 2, you get 4. All right? So the domain is all real numbers. And I'm going to write this in set builder notation here. And x is an element, that little e says an element of the real numbers. Where x is from negative infinity. X is from negative infinity to positive infinity. Okay, that's the set builder notation for that. Mainly what you want to focus on, x is this part of it. X can be from negative infinity to positive infinity. Okay? The range of this function, all right, is all of the y values that you can have. So the range is all of the y values that you're going to get out. Well, if I look at this, okay, it starts, if we look at the y-axis, it starts right here at 0, and then it goes all the way up. So our range here, but, negative values aren't going to happen. Okay, and that's because you're squaring something. So any number squared, whether it be a negative or a positive, is positive. So the range for this is y is an element of the real number. So y is just some real number, okay? And that is from 0, but it can equal 0, to positive infinity, okay? So it's all these numbers up here. And that's the range. let's move on to the next parent function. This is the square root function. Now, you might know that squares and square roots are inverses of each other, right? They undo each other. And that can be seen here graphically, because this happens to be half a parabola on its side, okay? And I'll get into why it's just half in a second. Okay? The shape, okay, so the shape of this is, I'll say it's parabolic, okay? In this case, we're restricting it, so it's half a parabola, but in general, I would say the shape is parabolic. Okay, it's on its side, doesn't matter. It still maintains those properties. Okay, the equation for this square root function is f of x is equal to the square root of x. Okay, nothing tacked on to it, just square root of x. Okay, this happens to be an inverse of the quadratic. Okay, now in order for it to pass the vertical line test, we can only have one output for every input. Now, if we were, as you know, if you square root something, a lot of times you'll put the plus minus. So if we had actually y is equal to plus minus the square root of x, and we included the minus square roots, we would get a full parabola. But in this case, we want it to be a function. We only want it to be the principal root or the positive square roots. So we're only going to deal with the positives, okay? So we want it to be a function and needs to pass the vertical line test. It needs to only be the principal root, okay? As far as the domain and range go, so the domain is a little bit different than the quadratic, okay? If you think about it, it's hitting the shadow that it's casting is on all these values. So it's there's no negative values coming out here, right? You can't plug in negatives. If you plug in a negative in the square root, you're going to get an imaginary number, not a real number, not on this graph. So, that being said, the domain are real numbers, okay? That double-lined R is real numbers, such that x is between 0 and infinity. Okay. Now the y value's out. The range of this. Well, we already talked about we restricted the range to be only positives. Okay. So that's what it's going to be, right? It's going to be all of these. Okay, this thing is going to gradually increase and cover all of our y values and put a shadow on all the y values, all the positive y values. So, we're going to say that y is an element of the reals, okay, and y actually also is going to be the same thing. Oh, you know what? This should be a y. I apologize. Y has to be between 0 and positive infinity, right? None of this stuff can happen. All right? None of that stuff is going to be output. All right? So that is the square root function. Let's move on. This is the function to the right here is called the cubic equation or cubic function. Okay? And I'm not sure, we'll call this shape a cubic, so the shape is a cubic. We'll notice that this doesn't have it sort of has y-axis symmetry, but it has really 180-degree symmetry. If you were to flip this over the y and then the x, okay? So if you flipped it twice over the y and the x, it would overlap. So that symmetry is, we call it 180 degrees symmetry, I don't know, something like that. But it's flipped over the y and the x value. Okay? As far as its equation goes, it's f of x is equal to x cubed. Okay, nothing else on it, just an x cubed. That's the driving, that cube is the driving factor of this shape. All right. Its domain. Actually, its domain and its range. I'll just put D for domain. Its domain is going to be all real numbers, right? I mean, you can plug in anything into this cubic. You can plug in any number, any real number you want, and you'll get some value out. So its domain, it's a real number, such that bar means such that. X can be between negative infinity and positive infinity. Okay. Again, this is set builder notation. The main focus is this right here. That's what really tells you what's going on. And the range is the same thing. Okay, it's covering all of the y values as well. You can get output any y value you want. So the range is almost identical except with a y. Oops. Keep on doing that. Okay. So the range is all real numbers. Okay. Let's move on to its inverse, the cube root function. So this is a cube root. Okay. Cube root function. Its shape, I guess, is a cubic. Okay, it's just on its side. Okay, all these inverses are just going to be on its side, actually reflected over the line y is equal to x. All right. Its equation is f of x is equal to the cube root of x. Okay, simple enough. It has the same symmetry. It's the same shape as our x cubed function. And again, its domain is going to be identical to the cubic. Okay, its domain and range. Actually, I won't even write it because this video is getting a little long. The domain and range for this cube root function is the same. It's all real numbers for both. Okay, you plug in, you can get any number out, and you can put in any real number in. All right, moving on. Okay, this is the absolute value function. Very similar to a linear function. However, whenever you plug in, a linear function would look like this, y is equal to x. However, whenever you plug in a negative value, it's going to turn positive, so it's going to be flipped up. So that's how you get this V shape. So, I don't know. There's no name for this shape. But maybe there is, but I don't know it. So we'll just go with equation. All right, the equation for this is f of x is equal to the absolute value of x. All right? Remember, very similar to the linear function y is equal to x, except it doesn't allow for negative y values. All right? The domain. Okay. Well, what does this cast a shadow on? Everything. Okay, you can plug in any number into any real number into the absolute value, and you get an output. Really, the positive version of that. So the domain is just going to be x is an element of the reals, such that x is between negative and positive infinity. All right. The range is a little bit different. Okay, we talked about the range. You can't get any negative outputs, right? It flips it up. It takes a linear function and flips it up to be positive. So the range here is going to only be positive numbers. So x is between, or y is between, sorry. Oops. 0 and positive infinity. Okay. So those are all the parent functions I want you to know. Now I want to go over a few transformations. All these transformations will be the same no matter if you use your if you're talking about absolute value function, quadratic, cubic, whatever. They're all going to be the same. So the example I'm going to use is a quadratic. And I want to talk about different things that we can do with this quadratic by tacking on different numbers. Okay? So the first transformation I want to talk about is a horizontal, horizontal meaning an up and down transformation. Horizontal transformation. Horizontal t, we'll call it. I don't feel like writing it out. Okay? If you take your parent function, in this case, x squared. So I'm just going to make a generic parent function like f of x. Okay, that's our parent function. If you tack on a number b onto this, okay, this shifts the function up b units. Okay, same thing if you subtract f of x minus b, this shifts down b units. Okay, so if we have our parent function and we say we have f of x is equal to x squared, that's our parent function, and we tack on a 2, okay? What this is going to do, it's going to shift this function up 2 units. So instead of our vertex being at the point 0, 0, now it's going to be at the point 0, 2. And I apologize for my drawing, but it's going to look something like that. It's going to be our parabola, but it's going to be shifted up 2 units. Okay. Same thing if we add a negative 2, it would shift down 2 units. That origin point, that vertex. Okay. The next shift I want to talk about is a vertical shift, vertical transformation, okay? And that is if we took our function and within the function we added b or subtracted b, okay? So if we add some number into the function, I'll explain exactly what that looks like in a second. This shifts to the left. It's kind of counterintuitive. You'd think plus would shift to the right, but it shifts to the left b units. And you guessed it, f minus b shifts to the right b units. Okay? So say we had our quadratic again. F of x is equal to, now in the parentheses here, normally we'd just have x squared. Now we're going to have x plus 2 squared, okay? What is this going to do? Think about the zeros of this function. You know that it's going to hit the axis at negative 2. So this is a shift to the left 2 units. So our parabola, instead of its turning point or its vertex being at 0, 0, it is now going to be at negative 2, 0. So it's going to look like that. Okay, it's shifting it to the left 2 units. All right, same thing if you added a negative 2, it would shift it to the right 2 units, okay? So that is a vertical transformation there. A few other things I want to talk about. This is actually a bad example for certain things. The parabola is because it's symmetric. Let's do flips. Flip over x-axis. Okay, so if we wanted this thing to flip over the x-axis, we would tack a negative 1 onto the function, okay? So an example of this would be f of x is equal to negative x squared. And what that would do, it would flip it over the x-axis, so it would look like this. All right. And this is a bad example, is a shift over the y-axis, or a flip over the flip over y-axis. Okay. And this is going to be, and you're not going to notice this because you're squaring it, but it's going to be a negative within just like this was within the squaring, this is going to be a flip over the y-axis. Since this is symmetric, you're not going to notice it. But an example of this would be f of x is equal to negative x squared, where you're actually taking the negative x and squaring it. Okay? Again, this was a poor example for this because you can't see it exactly. All right? You can combine these things. So if I had some function f of x is equal to x minus 2 squared plus 1, okay, that would be a shift to the right 2 units and a shift up 1 unit. Okay, so instead of our vertex or our vertex being at 0, 0, it is now at the point 2, 1. Okay, and that would be what it looks like. Okay. So there are other shifts. Okay, so we can stretch and shrink our parabola or any function we want. But since this video is already 21 minutes long, I'm going to save that for another video.